Hi, it's Matt, and in this video we're going to talk about the fifth postulate of quantum mechanics. But first, let's talk about the Hamiltonian operator, arguably the most important operator in all of quantum mechanics. So, the Hamiltonian operator we denote as H, as a capital H with the operator symbol over it, and in general can depend on spatial coordinates, momentum, and the time coordinate. So, let's talk a little bit more about it. The eigenvalues of the Hamiltonian operator are the measurable energies of the system, and its functional form is that the Hamiltonian, which I'm showing can depend on time, is going to be equal to t hat plus v hat, which is only a function of q of t. So just talk a little bit more. T hat is our kinetic energy, and then v hat is our potential energy operator, and in general, the potential energy can depend on both spatial coordinates and the time coordinate. So now that we know what the Hamiltonian is, we could talk about the fifth postulate of quantum mechanics. So up to this point, we've talked about what the wave function is and what we can do with it, but we haven't talked about how to get the wave function. That's what the fifth postulate tells us. It tells us that the wave function is the solution to the time-dependent Schrodinger equation shown here, which is that IH bar times the time partial derivative of the wave function is equal to the Hamiltonian operator applied to the wave function. And with the exception of some very special cases for the Hamiltonian, we cannot exactly solve the time-dependent Schrodinger equation to get an exact wave function. And in those cases, we would approximate it, but we're not going to talk about that here. So first, let's talk specifically about the case of time-independent Hamiltonians. So for a time-independent Hamiltonian, solutions of the time-dependent Schrodinger equation can be found using the separation of variables. And what that means is psi q of t, our total wave function, can be separated into a spatial part, which we'll call lowercase psi of q, q being our spatial coordinates, times this function here of only time. And when the solution is of the above form, we find the following, where E is the energy. We find that IH bar, then the time derivative of the time component of our wave function, is equal to E times the time component of our wave function. And when we solve that differential equation, we get that the time part of our wave function is e to the negative IET over h bar. But then when it comes to the spatial part, we get h bar psi q of q is equal to E, our energy, times psi of q. I'm not going to go over in this video how exactly we get these from the separation of variables. I'm going to release another video with this one that will explain that process. But moving forward, let's talk about that second equation, which is our time-independent Schrodinger equation. And we notice it's an eigenvalue relationship. And the solutions of the time-independent Schrodinger equation, again, this equation here, are the stationary states of the system. So what are stationary states? Stationary states are the solutions to the Schrodinger equation where the probability distribution and the expectation of value of operators are independent of time. So we could think of this physically as a standing wave from classical physics. So again, probability distribution and expectation values do not change with time. They're fixed. And the energies of the stationary states are the only energies that could be measured. And again, that comes from our time-independent Schrodinger equation being an eigenvalue relationship, just like those we talked about with the third postulate of quantum mechanics. So the exact form of our spatial wave function, psi of q, will be determined by the specific Hamiltonian. So let's talk a little bit more about this. To start off, let's put this together. So for a single stationary state, we have that the wave function of the stationary state is the spatial component of our stationary state times the time component. Again, psi of q, our stationary state, is determined by our particular Hamiltonian, but then regardless of the Hamiltonian, the time component will be e to the negative IET over h bar, where E is the energy of our stationary state. But for our particular system, we're likely going to have multiple stationary states for that Hamiltonian. And we'll index these psi1 of q, psi2 of q, psi3 of q, and so on. And these states don't necessarily have the same energy. In fact, they very likely have different energies. So each of these stationary states has its own time component that the energy is indexed. We have E1, the energy of the first stationary state, E2 for the secondary stationary state, and E3 for the third, and again, so on. So that means that for the wave function of a particular stationary state, we're going to want to index it by k. So psi k of qt is going to be equal to psi k of q e to the negative I e k t over h bar. Again, k is just the index for the stationary solution. So now that we have the functional form of the wave function for a particular stationary state, we need to go a little bit further. When we have a time-independent Hamiltonian, the stationary state solutions are not the only possible solutions of the time-dependent Schrodinger equation. And in fact, any linear combination of these stationary states with their corresponding time component will be a solution. So that means for a particular time-independent Hamiltonian, the complete solution to the time-dependent Schrodinger equation given to us by the fifth postulate of quantum mechanics is psi q of t is the summation across k, the summation across all of our stationary states of the stationary state with its corresponding time component with a coefficient in front, ck. Again, that's just the coefficient of each particular stationary state in the summation. And the values of these ck's, our coefficients, is dependent on the system, but we will always choose our ck's such that our overall wave function is normalized. With that, that's all I have. Thank you so much for listening. Leave any questions you have below, and have a great day.